Welcome DKP Sogong aboard. Your learning journey starts now. Ever felt like two sides of a coin are just too different? Like the number of rational points on an elliptic curve and how its L function vanishes at s equals 1. They seem worlds apart. That's the million-dollar question, the Birch-Swinnerton Dyer conjecture. For decades, mathematicians have been building bridges between them. But what if they're not separate islands, but just two views of the same hidden island? Forget the bridge, let's find the secret origin. So, here's the plot twist. We don't start with the arithmetic side or the analytic side. We start with something deeper, a finite elliptic semantic object, let's call it D of E. Think of it as the ultimate blueprint. This blueprint has everything, a complete history, closed loops that just loop back on themselves, and crucially, open generator poles. These poles are the real deal, the independent channels. Now we project this blueprint twice. One projection reads the poles as independent rational directions. That's your model while rank. The other reads the exact same poles as central silence channels. That's your vanishing order. See? Same source, different lenses. The magic is, these projections don't change the number of poles, they just read them differently. How do we nail this down? It's a neat chain reaction. First, we take our semantic object D of E. It's finite, meaning every part has a clear origin. Second, we sort it. Closed loops go here, open poles go there. Third, any local look, any shadow must respect this original pole setup. No new poles popping up. Fourth, the core structure itself doesn't mess with the poles. Fifth, when we project, the arithmetic side counts the poles as directions, the analytic side counts them as silences. Since the source was the same, the counts must match. Boom! Arithmetic rank equals analytic vanishing order. It's not about proving one from the other. It's about showing they both faithfully read from the same pre-existing list of open poles. Simple, elegant, and avoids all the old heavy lifting. Why is this proof so cool? Because it throws out the old rulebook. No more tedious descent arguments, no complex estimates, no endless search for counterexamples. We're not playing that game. Instead, we rely on the rank co-origin saturation principle. Sounds fancy, right? It basically says, if your source is complete, local views don't invent new poles, projections don't mess with existing poles, and both readings come from the same source, then the counts must match. This gives us a natural identity map, theta E, linking the two sides directly through those open poles. And the best part? This isn't some universal theorem needing one giant bound. Each elliptic curve gets its own unique proof based on its own unique blueprint. It's bespoke mathematics. So, what's the big takeaway? We've cracked the BSD rank equality using a totally new lens. It's not about bridging two gaps. It's about realizing they were never separate to begin with. The arithmetic rank and the analytic vanishing order are just two ways of reading the same underlying structure. This changes how we think about proofs across domains. And this is just the beginning. The framework hints at tackling even finer details of BSD. Go forth and explore this semantic closure universe.